welcome to this problem walkthrough. Today, we'll be exploring LeetCode problem number 1560, titled Most Visited Sector in a Circular Track. This is an interesting problem that challenges our understanding of circular sequences and efficient counting techniques. Let's dive right in and uncover the solution together. Imagine a circular running track with n sectors, numbered sequentially from 1 to n in a clockwise direction. A marathon runner starts at a specific sector and follows a sequence of moves represented as an array called rounds. Each element in this array indicates the starting and ending sectors for each lap. The runner moves sequentially through the sectors, and because the track is circular, if they are at sector n, the next sector would naturally be 1. Now, your objective is to determine which sectors the runner visited the most during the marathon. If there are multiple sectors with the same maximum visit count, you must return those sectors in ascending order. The problem defines the input and output formats clearly. You'll be given n, the total number of sectors, and a list rounds with the sequence of starting and ending points for the laps. The output should be a sorted list of the most visited sectors. Let's explore some examples to better understand how this works. In the first example, the input specifies n equals 4, meaning there are 4 sectors on the track, numbered 1 through 4. The rounds array is 1, 3, 1. The runner starts at sector 1, moves to sector 3 during the first lap, and then returns from sector 3 to sector 1 in the second lap. To break it down, during the first lap, the runner visits sectors 1, 2, and 3. During the second lap, they visit sectors 3, 4, and 1. Combining these visits, sectors 1, 2, and 3 are visited the most. Thus, the output is 1, 2, 3, sorted in ascending order. This demonstrates how the runner's path is traced, and the most visited sectors are determined. In the second example, the input specifies n equals 7, meaning there are 7 sectors on the track. The rounds array is 2, 5, 2. Here, the runner starts at sector 2 and moves to sector 5 during the first lap. In the second lap, the runner goes from sector 5 back to sector 2. Let's outline the visits. During the first lap, the runner visits sectors 2, 3, 4, and 5. In the second lap, the runner visits sectors 5, 6, 7, 1, and finally 2. When combining these visits, the most visited sectors are 2, 3, 4, and 5. Therefore, the output is 2, 3, 4, 5, again sorted in ascending order. This clarifies how the runner's path over multiple laps determines the result. In the third example, the input specifies n equals 2, meaning the track consists of just 2 sectors. The rounds array is 2, 1, indicating that the runner starts at sector 2 and moves to sector 1 in just 1 lap. This is straightforward to trace. The runner visits sectors 2 and 1 during this lap. Since the track only has 2 sectors, both 1 and 2 are visited the most. The output is 1, 2, sorted in ascending order. This example highlights how even with a small number of sectors, the solution must account for the circular nature of the track. Let's now consider some constraints and edge cases. First, if the track has only one sector, such as when n equals 1, the result will always be 1, since the only sector is visited repeatedly. For a single lap, where the length of rounds is 2, the result will include all sectors visited from the starting sector to the ending sector, inclusive. When the number of sectors is at its maximum, n equals 100, the solution must efficiently handle the large range of possible sectors. Similarly, when the length of rounds is at its maximum, 1000, it's crucial that the solution processes the large number of moves without exceeding time limits. These considerations ensure the solution remains robust and efficient across a variety of inputs. To tackle the problem of finding the most visited sectors in a circular track, we explored several approaches, starting with the brute force method. The main idea behind this approach is to simulate the exact movement of the runner as they traverse the circular track, sector by sector. For this, we use an array called visits to keep account of how many times each sector is visited. By iterating through pairs of consecutive sectors in the rounds array, we simulate the transition from the starting sector of one round to the ending sector, wrapping around the track whenever necessary. After completing the simulation, the sectors with the highest visit counts are identified as the result. However, while this approach is straightforward and easy to understand, it comes with significant drawbacks. Specifically, it becomes computationally expensive for large inputs because it explicitly simulates every step of the runner's movement. The time complexity depends on both the number of sectors, n, and the total number of steps, k, making it inefficient for scenarios with a high number of transitions. A more efficient solution is the optimized approach, which avoids simulating each step and instead focuses on analyzing the transitions between sectors. The key insight is that we can determine the range of sectors visited during a transition without explicitly counting every intermediate step. By leveraging modular arithmetic, we account for the circular nature of the track, ensuring that transitions wrapping around from the last sector to the first are handled seamlessly. For each pair of consecutive sectors in the rounds array, we simply compute the range of sectors that are visited. Since all sectors in the range are guaranteed to be visited, we can directly focus on identifying the most visited sectors. This approach is not only computationally efficient but also simplifies the problem dramatically by reducing it to an analysis of boundaries rather than individual steps. With this method, the problem scales linearly with the number of transitions, and the use of constant space ensures minimal memory usage. The optimized approach is elegant and powerful, making it an excellent choice for this type of problem. Ultimately, the optimized approach was selected as the final strategy for solving this problem. It provides a significant improvement in efficiency by avoiding the unnecessary simulation of every step, focusing instead on the transitions and ranges directly. The use of modular arithmetic elegantly handles the circular nature of the track without requiring additional complexity. Moreover, it eliminates the need for extra memory to store visit counts, making it highly space efficient. While the brute force method is conceptually simple, its inefficiency for larger inputs makes it impractical. In contrast, the chosen strategy strikes a balance between clarity and performance, leveraging the structure of the input to solve the problem efficiently. By focusing on the most critical elements of the problem, this approach ensures that we achieve the desired result in an optimal manner, making it the ideal solution for this challenge. The problem, most visited sector in a circular track, involves finding the sectors on a circular track that are visited the most after a series of rounds. The track consists of sectors numbered from 1 to n. Given a starting sector and a sequence of movements, the player moves sequentially, and if they reach the last sector, they wrap back around to the first. Our goal is to return the list of the most visited sectors in ascending order. To solve this efficiently, we start with input parsing. The input includes the total number of sectors, n, and a list called rounds. This list specifies the starting sector and the sequence of endpoints for each round. The key observations here are that movement is always sequential and that wrapping around the track is part of the movement. For example, moving from sector 4 to sector 2 involves visiting 4, 5, 1, and 2. Based on the starting and ending points, we can deduce which sectors are visited most frequently without explicitly counting visits to each sector. The first sector of every round and all intermediate sectors visited while moving to the next round are guaranteed to be visited at least once. To implement the algorithm, we begin by extracting the start sector, which is the first element of rounds, and the end sector, which is the last element. If the start sector is less than or equal to the end sector, the player visits all sectors in order between these 2 points inclusively. For instance, starting at sector 3 and ending at sector 5 results in visiting sectors 3, 4, and 5. However, if the start sector is greater than the end sector, the player wraps around the track. In this case, the visited sectors include all those from the start sector up to sector n, followed by sectors 1 up to the end sector. For example, starting at sector 4 and ending at sector 2 involves visiting 4, 5, 6, 1, and 2. The output is the list of visited sectors, which are naturally in ascending order due to the sequential traversal. By leveraging the circular nature of the track, we avoid unnecessary computations, making the algorithm more efficient. The data structures used in this solution are straightforward. The rounds array represents the starting and ending points for each round, while the output is a list of the sectors visited, constructed directly in ascending order. The time complexity of the algorithm is O(k), where k is the number of sectors visited during the traversal. This is because we visit each sector in a single pass. The space complexity is also O(k), as it depends on the size of the output list containing the visited sectors. We also need to handle edge cases. If there is only one sector, it is visited repeatedly, so the output is simply 1. If the movement involves a full circular wrap, such as from sector N to sector 1, all sectors are visited in sequential order. For minimal inputs, like n equals 3 and rounds containing only 2, 2, only the start sector is visited. These edge cases ensure that the algorithm handles all possible scenarios robustly. For example, with n equals 4 and rounds equals 1, 3, the player starts at sector 1 and moves sequentially to sector 3, visiting sectors 1, 2, and 3. All of these are visited once, so the output is 1, 2, 3. Another example is when n equals 4 and rounds equals 3, 1. Here, the player starts at sector 3 and wraps around the track to reach sector 1. In this case, the visited sectors are 3, 4, and 1. All of these sectors are visited once, and since we need the output in ascending order, the result is 1, 3, 4. The Python implementation of the algorithm is both concise and efficient. By leveraging the sequential movement of the player, we directly construct the list of visited sectors. If the start sector is less than or equal to the end sector, we use the range function to generate the list. Otherwise, we handle the circular wrap by combining two ranges, one from the start sector to n and the other from 1 to the end sector. This ensures that the algorithm is both simple and efficient, effectively solving the problem in linear time while maintaining clarity in the code. This Python implementation efficiently solves the problem of finding the most visited sectors in a circular track. The function most_visited takes two inputs, n, the number of sectors, and rounds, a list of integers representing the sequence of sectors visited during rounds. First, we check if the start and end sectors of the rounds are the same. If they are, only that sector is visited, so we return it as a single element list. This is handled by the condition if rounds 0 equals rounds dash 1. Next, we check if the start sector is less than or equal to the end sector. If this is true, it means the traversal does not wrap around the circular track, and the most visited sectors are all those in the range start, end. This is computed using Python's range function and returned as a list. If the traversal wraps around the circular track, we handle it by combining two ranges, start, n, from the start sector to the last sector, and 1 and end, from sector 1 to the end sector. These ranges are concatenated and returned as the list of most visited sectors. This approach ensures that the solution is both efficient, O1, computation for constructing ranges, and concise, while correctly handling all edge cases such as single sector visitation or circular wrapping. Here, we start by importing the necessary packages and defining our solution class. The core method, most_visited, takes two parameters, n, representing the total number of sectors in the circular track, and rounds, an array that contains the sequence of sectors visited during the race. First, we handle a simple edge case. If the starting sector and the ending sector are the same, it means only one sector is visited throughout, so we return a list containing just that sector using collections.singletonList. Next, we declare a result list to store the most visited sectors. Now, if the starting sector is less than or equal to the ending sector, this means the path does not wrap around the circular track. In this case, we iterate through the range of sectors between start and end, inclusive, and add each sector to the result list. However, if the starting sector is greater than the ending sector, the path wraps around the circular track. To handle this, we first add all sectors in the range from start to n, which represents the sectors from the starting point to the end of the track. Then, we loop back to the beginning of the track and add all sectors in the range from 1 to end. This ensures we capture all sectors visited during the wraparound. Finally, we return the result list containing all the most visited sectors. This approach ensures we correctly handle both linear and circular traversals of the track in an efficient and clear manner. To begin with, we're looking at a basic case where the path does not wrap around the circular track. The input specifies n equals 4, meaning there are 4 sectors on the track and the rounds array is 1, 3. This tells us the race starts at sector 1 and ends at sector 3. First, we note the starting sector, rounds, 0, which is 1, and the ending sector, rounds, dash 1, which is 3. Since these two values are not equal and the start sector is less than or equal to the end sector, we know the path is sequential and does not involve wrapping around the track. In this case, the most visited sectors are simply all the sectors between the start and end, inclusive. Using the range function, range 1, 3 plus 1, we get the list 1, 2, 3 as the result. This means sectors 1, 2, and 3 are the most visited. The output for this example is 1, 2, 3. Now, let's consider a case where the path wraps around the track. Here, the input specifies n equals 4, with sectors 3, 1. This means the race starts at sector 3 and ends at sector 1. First, we identify the starting sector, rounds 0, which is 3, and the ending sector, rounds -1, which is 1. Since the start sector is greater than the end sector, we know the path wraps around the circular track. To determine the most visited sectors, we divide the path into two ranges. The first range is from the starting sector, 3, to the end of the track, which is range 3, 4 plus 1, producing 3, 4. The second range starts from sector 1 and goes up to the ending sector, which is range 1, 1 plus 1, producing 1. Combining these two ranges gives us 3, 4, 1. Therefore, sectors 3, 4, and 1 are the most visited in this case. The output is 3, 4, 1. Finally, let's examine a scenario where only a single sector is visited. In this example, n equals 3, and the rounds array is 2, 2. Here, the race starts and ends at the same sector, which is sector 2. First, we note that rounds 0 and rounds -1 are both equal to 2. Since the start and end sectors are identical, we know that the only sector visited during the race is sector 2 itself. In this case, there's no need to calculate ranges, as no other sectors are involved. The output is simply 2. This highlights that when the start and end sectors are the same, the result directly corresponds to that single sector. Additionally, we've now seen how the problem handles three scenarios: paths without wrapping, paths with wrapping, and paths where only one sector is visited. These insights can help us generalize the solution for any input. This slide focuses on the time complexity of the solution. The first operation to consider is the initial equality check, where we determine if the start and end sectors, represented by rounds 0 and rounds -1, are the same. This is a simple comparison that runs in constant time, or O1. Next, we handle the scenario where the path does not wrap around the circular track. In this case, the range of visited sectors is calculated using the range function, spanning from rounds 0 to rounds -1 plus 1. The time required to generate this range depends on the number of sectors included, which is k equals rounds -1 rounds 0 plus 1. Therefore, this operation takes k time. These two steps form the foundation for analyzing the time complexity of the solution. When the path wraps around the circular track, the computation involves generating two separate ranges. The first range starts from rounds 0 and goes up to n plus 1, while the second range begins at sector 1 and continues to rounds -1 plus 1. The length of the first range is determined by the formula n rounds 0 plus 1, and the second range has a length equal to rounds -1. Adding these together gives the total number of visited sectors as n rounds 0 plus 1 plus rounds -1. Generating both ranges takes time proportional to the total number of elements, which is k, where k represents the total sectors visited. After that, the range objects are converted into lists using the list function, which also requires k time since it processes each element in the ranges. In the worst-case scenario, all sectors are visited, making k equal to n. Consequently, the overall time complexity simplifies to n, ensuring efficient handling of the input parameters. Now turning to space complexity, we analyze the memory usage of the solution. The input list rounds occupies m space, where m is the length of the list. This is because the input needs to be stored in memory for processing. The output, which is a list of the most visited sectors, can contain up to n elements in the worst case. This results in an additional space requirement of k, where k is the number of sectors in the output list. Additionally, the range objects used during computation are lightweight and do not significantly contribute to memory usage, as they are iterators and not fully materialized in memory. Thus, the dominant factor in space usage is the output list, leading to an overall space complexity of k. Simplifying for the worst case where all sectors are visited, the space complexity becomes n, ensuring the solution's efficiency even for large input sizes. In comparison to a brute force approach, the optimized solution demonstrates significant improvements in both time and space complexity. A naive method would involve simulating the traversal of the circular track for each round and maintaining a count of visits for all sectors. This would result in a time complexity of O(m*(n), where m is the length of the rounds list, and n is the total number of sectors. The space complexity in such a case would be O(n), due to the storage required for the count array. On the other hand, the optimized solution avoids unnecessary simulations by directly calculating the most visited sectors using mathematical operations, reducing the time complexity to O(n), while maintaining the space complexity at O(n). The direct use of range-based calculations ensures that the execution time grows linearly with the number of sectors. This mathematical approach highlights the efficiency of the solution, making it well-suited for handling large inputs effectively. In this problem, there are a few common mistakes to watch out for. First, misinterpreting the circular track is a frequent issue. Remember, if the sectors are numbered 1 through n, the track wraps around, meaning moving from sector n back to sector 1 is valid. Misunderstanding this can lead to incorrect results. Another error is off by 1 issues when counting sector visits. It's important to include both the start and end sectors exactly once for each round, without double counting or skipping. Beginners may also overcomplicate the solution by simulating every step of the rounds, which is unnecessary and inefficient. Instead, you can calculate the visited ranges directly using modular arithmetic, which simplifies the logic and improves performance. Additionally, some forget that the problem requires returning tide sectors in ascending order. Missing this condition can lead to a wrong answer. Finally, for large inputs, iterating through every sector for every round can become a performance bottleneck. A more optimized approach focuses only on the specific range of sectors visited in each round, avoiding redundant computations. This problem is a great opportunity to showcase your skills in handling circular data structures and modular arithmetic. These concepts are not only essential here but also appear in many other technical problems. When optimizing your solution, emphasize how you reduce unnecessary iterations such as calculating ranges directly instead of simulating each step. This demonstrates an understanding of time complexity, which interviewers appreciate. Don't forget to address edge cases, such as when there's only one round where the start and end sectors are the same, or when the track size is minimal, such as n=1. Large inputs near the constraints, like when the number of rounds is very high, are also worth discussing. Highlighting trade-offs, such as comparing a brute force method to an optimized solution, can show that you understand the strengths and limitations of different approaches. This level of insight is often what sets apart strong candidates in interviews. If you want to deepen your understanding of similar problems, consider exploring some related LeetCode challenges. For example, LeetCode 1822, sign of the product of an array, involves modular arithmetic and working with ranges, which ties directly to the concepts used here. LeetCode 457, circular array loop, is another problem rooted in handling circular data structures, requiring careful attention to boundaries. While LeetCode 1704, determine if string halves are alike, isn't circular, it emphasizes splitting and counting efficiently, which is a transferable skill. Lastly, LeetCode 846, hand of straights, focuses on modular arithmetic and counting within ranges, offering valuable practice for mastering these techniques. These problems can help you build intuition and confidence when tackling variations of circular or range-based scenarios. To solve this problem, there are a few approaches to consider, each with its pros and cons. The brute force approach involves simulating each round step by step, iterating through each sector that's visited. While simple to implement, the time complexity of O(n*(m) makes it impractical for large inputs. A better alternative is the optimized range counting approach. Here, instead of simulating every step, you calculate the range of sectors visited during each round and update the counters directly. This method reduces unnecessary iterations and achieves a time complexity of O(m). Another option is using a prefix sum array to track visits more efficiently. While this can be helpful for problems with large ranges, it does require additional space. Finally, modular arithmetic is key to handling the circular transitions on the track. By leveraging modular arithmetic, you can simplify computations and avoid redundant checks, making your solution both cleaner and faster. Understanding these trade-offs is essential for selecting the best approach for different scenarios. Great work! To summarize, we tackled the most visited sector in a circular track problem using a modular arithmetic approach. We examined key takeaways like handling circular data and optimizing for performance. Thanks for joining, and be sure to check out more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!